All right, I want you to take a second and travel back with me, way back, to the ancient, forgotten era of the early 2020s.
Oh boy, are you sure?
I know, it's a bit of a cursed timeline. But think past the sourdough starters and the Tiger King marathons. Do you remember the sound?
Or more like the lack of sound.
Exactly. The silence. I remember walking down a huge avenue in my city, middle of the day, and it was just dead quiet. It was so surreal.
It's eerie. And the visuals, too.
Right, the whole nature's healing thing, all those memes. You saw the pictures of the clear canals in Venice, the smog over LA just
The
vanishing.
Himalayas. People could see the Himalayas from 100 miles away.
Yeah, and we all sort of patted ourselves on the back like, okay, this lockdown is terrible, but hey, at least the atmosphere is getting a little break.
It was a nice thought, a comforting story. We stop so the planet breathes easier.
But because this is the Deep Dive Lab, you know there's a huge plot twist coming. And this isn't just some minor detail. This is a massive atmospheric whodunit. While we were all looking at clear skies, something invisible was happening that was, well, frankly, it was terrifying.
Terrifying and, for a while, just completely baffling. I mean, CO2 emissions dipped a bit, which is what you'd expect, right? But methane did the exact opposite.
It didn't just go up, it went vertical. We're talking a record-shattering surge. In 2020, the growth rate hit 16.2 parts per billion per year.
Which is the fastest rise we have ever recorded, ever. It just broke all the models.
So welcome to the Deep Dive. Today, our mission is to crack this case. We're digging into a brand new paper just out this month in Science. It's called Why Methane Surged in the Atmosphere During the Early 2020s.
And it's this incredible piece of detective work from a huge team led by people like Philippe Sieyès and Xu Peng from places like Peking University and the top climate labs in France.
They basically put together the Avengers of atmospheric science to answer this one question. If humanity pressed pause, why did methane hit the accelerator? Was it cows? Gas leaks? Or was it something way, way weirder?
And the answer, it turns out, really forces us to rethink what pollution even is. It wasn't just about what we put in the air, but what we stopped putting in the air.
Okay, let's get right into that, because that is the part of this paper that just made my jaw drop.
Okay.
I honestly thought it was a typo. You're saying that cleaning up the air made a greenhouse gas problem worse.
For a little while, yes. It's this incredible paradox. To get it, you have to stop thinking about the atmosphere as just a big empty box. It's a giant chemical reactor, and we have to talk about its detergent.
The detergent. I love that analogy. Break it down.
Okay, so imagine the atmosphere has this built-in cleaning crew. The main chemical on that crew is called the hydroxyl radical, just OH for short.
Okay.
And OH is like a little piranha. Its job is to find pollutants, like methane, and just rip them apart. It oxidizes them. It scrubs them out of the air.
So it's like the Pac-Man of the sky, just chomping on methane ghosts.
That's a perfect way to put it. It's the atmosphere's immune system. But here's the catch. This Pac-Man, this OH radical, it isn't just there. The atmosphere has to make it. And the recipe needs a few ingredients. It needs sunlight, water, and this is the critical part. It needs nitrogen oxides, NOx.
Oxide. That's car exhaust, isn't it?
That's the stuff. It's the classic pollutant from tailpipes, power plants, factories. It's what makes city smog that awful brown color. It's bad for your lungs, no question.
I think I see where this is going, and it feels deeply ironic.
It's the ultimate atmospheric irony. When the world locked down, what disappeared? Traffic, industry. NOx emissions just fell off a cliff.
Yeah.
Globally, down like 10–15% in some places.
But by getting rid of the smog,
Yeah.
we took away the key ingredient for making the Pac-Man.
That's the mechanism. We stopped pumping out NOx, so the atmosphere's detergent factory slowed way down.
Oh, man. So all the methane that was already up there suddenly had a much longer lifespan. There was nothing to clean it up.
Exactly. We talk about sources and sinks. The source is the faucet, the sink is the drain. What happened in 2020 is that the drain got seriously clogged.
And how much of the problem was this clogged drain?
It was huge. This new paper calculates that this lack of detergent, the drop in OH, accounts for about 80–83% of that record-breaking surge.
80%. That's almost all of it. So this wasn't really about us putting more methane out there.
Not primarily, no. It was mostly that the atmosphere's ability to clean itself was temporarily crippled.
That is such a wild, be careful what you wish for a moment. We got the clean air we wanted, and in doing so, we accidentally let methane run wild.
It really shows you how interconnected everything is. You can't just turn one knob in the Earth system without, checking all the other dials. We've been sort of masking methane's real impact with our own smog.
So the monster was in a cage made of our own pollution.
That's one way to put it, yeah. But the clogged drain only explains most of the story. The sea ice and Peng paper makes it clear something else was going on, too. There was also new methane being added.
Right, that other 20%. If the detergent running out explains why methane stayed longer, something was still pouring more in.
Correct. And to find that culprit, we have to look away from the empty cities and out into the wilderness.
Okay, Chapter 2, The Wet and the Wild.
So while we were all stuck inside, the planet's climate was doing its own thing. From mid-2020 all the way to mid-2023, we were in what's called a triple dip La Niña, a really long one.
I remember hearing about that. La Niña means cooler oceans in the Pacific, which I always connect with, like better snow for skiing out west.
It does, but it messes with weather patterns everywhere. And for the tropics, La Niña basically meant one thing: rain. A lot of rain.
And what loves warm, wet conditions?
Microbes. Specifically, these little methane-producing microbes that live in wetlands and swamps. You dump a ton of water on them, the swamps expand, and these little guys they go into overdrive.
They're having a feast.
A huge feast. They eat up all that wet organic matter in the mud, and they burp out methane.
The swamp thing was adding to the problem.
A lot. And what's so cool is that the satellite data they used from the Japanese GOSAT satellites could actually see where it was happening. It wasn't everywhere. It was specific hotspots.
Oh, say so where?
The paper calls them out. The Sud wetland in South Sudan, one of the biggest in the world, the Cuvette Centrale in the Congo, and huge parts of Southeast Asia. These places basically lit up with methane emissions.
So while the highways in America were quiet, the swamps in Africa were having a massive party.
You could say that. And we saw it in the Arctic, too, where warming is waking up those microbes. But what's interesting is the Amazon.
What happened there?
It was the opposite. That same La Niña pattern actually caused drought in parts of the Amazon, so wetland emissions there went down. It just proves how much these big weather patterns can shift methane production around the globe.
Okay, so I'm with you. We've got a broken washing machine because there's no detergent, and we've got supercharged swamps making a huge mess. But I have to be the skeptic for a second.
Go for it.
How do they really know? I mean, 2020 was chaos. Maybe some big gas field was leaking and nobody noticed. How are they so sure it was swamps and not, fossil fuels?
That is the perfect question. And it brings us to the coolest part of the study, Chapter 3, the fingerprints.
Ah, the forensic evidence. Give me the CSI, atmosphere breakdown.
Okay, so this is where it gets amazing. Not all methane is created equal. It comes in different chemical flavors based on the carbon atom at its core. We call them isotopes.
Like carbon-13.
Exactly. So you have your normal lighter carbon-12, and then you have this slightly heavier version, carbon-13.
Right. Light versus heavy.
Now, methane that comes from fossil fuels, a natural gas leak, a coal mine, that carbon's been cooked underground for millions of years. It tends to be heavier. It has more carbon-13.
Okay, heavy equals fossil fuels. Check.
But the microbes in a swamp, they're metabolically lazy. They prefer to process the lighter carbon-12. It's just easier for them. So methane from biology, from a swamp or even a cow's stomach, is isotopically lighter.
So light equals life, or, rotting life.
Exactly. So the scientists looked at the air samples from all over the world. They measured this ratio. If the surge was from secret fossil fuel leaks, the atmosphere should have gotten heavier.
And what did it do?
It got lighter, significantly lighter. That's the smoking gun.
Wow. Case closed.
Pretty much. It proves the new emissions were overwhelmingly from microbial sources, from the wetlands, not from industry.
That's incredible. It's like the atmosphere keeps a receipt, and this one said swamp gas. But this gets to another thing in the paper, this idea of bottom-up versus top-down science. What does that mean?
This is a huge point. It explains why everyone was so surprised by this. Bottom up is when you try to estimate emissions from the ground.
Like counting things.
Right. You say, okay, we have this many cows, this many rice paddies, this many gas wells. You add it all up on a spreadsheet.
And top down.
Is looking from space with a satellite and measuring what's actually in the atmosphere.
And let me guess, the spreadsheet didn't match what the satellite saw.
Didn't even come close.
Yeah.
The bottom-up models totally missed this. They completely underestimated how much methane those wetlands would pump out when they got that much rain.
That's a little scary. It means our counting systems for the planet are wrong.
It's a wake-up call. It tells us we can't just rely on estimates on paper. We need that top-down view from the satellites to see the real picture, especially when nature does something unexpected.
So we have this perfect storm then, 2020 to 2022. We killed the atmospheric cleaner by staying home, and nature cranked up the methane faucet because of La Niña.
And the isotopes proved the source, a perfect conspiracy of chemistry and biology.
But the paper goes up to 2023. Did things get better?
They did. This is Chapter 4, the recovery. By 2023, that crazy growth rate had dropped by about half, down to around 8.6 parts per billion.
Still high, but way better than 16.
Exactly. And it makes perfect sense with their theory. What happened in 2023?
We all went back to work. The traffic came back.
The traffic came back. NOx emissions went back up. The atmosphere's detergent factory started running again. And at the same time, that triple dip La Niña finally ended, so some of those wetlands started to dry out a bit.
So when the causes went away, the effect went away. It proves the whole theory.
It really does. It all fits together perfectly.
So, okay, let's bring this all home. What does this mean for us now? Beyond just being a fascinating story, what are the big takeaways?
Yeah.
Because this feels heavy.
It is. I think there are three really big ones.
Give me number one.
First is what we're calling the COVID paradox. It just proves that our air pollution has been masking some of the true warming effect. Those pollutants like NOx, they're terrible for our lungs, but they're accidentally creating this chemical shield for methane.
Which puts us in a really tough spot.
Yeah.
We have to clean up the air for public health.
But when we do, we unleash the full potency of methane. We have to be ready for that.
Wow. Okay. What's number two?
The technology gap. We can't trust the spreadsheets anymore. The bottom-up accounting failed. If we're going to have global agreements to cut methane, we have to be able to verify them from space. The satellites are non-negotiable now.
Because otherwise we'd be flying blind. We would have thought everything's getting better during the pandemic when it was actually getting worse.
Totally blind. And the third, maybe the most important, is nature's feedback. We just got a huge warning shot about how sensitive the planet is. A couple of years of extra rain in the right places triggered a massive methane burst.
Something we have absolutely no control over.
None. And as the world gets warmer, we expect more of these extremes, more intense rains, more thawing permafrost. Nature could start adding methane way faster than we can cut it.
It's just so complex. You pull this one little lever over here, traffic, and this whole other part of the machine starts spinning out of control.
Which leads to the really big, provocative question this study leaves us with.
Okay, let's hear it.
We are all moving toward a cleaner future. Electric cars, clean energy, that's a good thing. We want less smog.
Of course. I want to breathe. We all do.
But this study proves that as we achieve that, as we get rid of NOx, we are permanently getting rid of the atmosphere's cleaning agent for methane.
So cleaner air means methane lasts longer. Period.
Exactly. So if that's the future we're building, it means our current targets for cutting methane emissions from, say, agriculture and energy, they might not be nearly ambitious enough.
Whoa.
Think about it. All our climate goals are based on the atmosphere working a certain way. If we're about to change a fundamental part of its chemistry, we might have to cut our methane emissions way, way faster just to stay in the same place.
We have to overcorrect to make up for the help our own pollution was accidentally giving us.
Precisely. It really raises the stakes.
Well, on that incredibly sobering but enlightening note, I think we have to wrap up our investigation.
It's a stark reminder, isn't it? In the Earth system, there's no such thing as a free lunch.
No free lunches, just a very complicated methane bill coming due. A massive thank you to Felix CH₄, Shushi Peng, and their whole team for this amazing detective work.
And for giving us the tools to finally understand what on earth was happening in those years.
And thank you for joining us in the Deep Dive Lab. If you enjoyed solving this atmospheric mystery, you know what to do. Smash that subscribe button so you don't miss the next one.
Until then, keep asking questions.
See you in the next Deep Dive.